Hi, everyone. Welcome to this first episode of our 5th climate seminar series that we're going to kickstart today with our guest speaker, Larryn Diamond. I'm Charmilino, I'm project manager at Climate, and I'm only going to be introducing the seminar today because we have Alana Brett and Alexandra Kouchner, 2 researchers from UNIN and EPFL, who are going to moderate the session today for us. And they are experts in geology, so they're in a much better position than I am to ask efficient and interesting questions. So the seminar is going to be hosted in a hybrid format, both on UNIL at EPFL campus, and on Zoom. For people who wants to ask questions, there are going to be more than one opportunity during the presentation. So you can either write your questions in the chat, or you can also raise your digital hands when the time comes to ask your questions. And here in person, we're going to circulate with a microphone so you can ask your questions. I'm going to leave the floor for Alana Brett to introduce our guest speaker.
Great, so welcome from my side to everyone in person and on Zoom. Hello, there's the camera out there. Yes, my name is Alana Brett. I'm a researcher at UNIL in the structural geology group, and I work on projects on geothermal. And today it's my pleasure to invite Larryn to the floor. And Larryn is has been a full professor in rock-water interaction group at the University of Bern in the Institute for Geological Sciences for many years now, since 2002. He's also held a full professorship in Leoben in Austria before that, and has done postdocs in Canada as well, and originally hails from New Zealand. And Larryn will be speaking to us today about his wealth of knowledge and experience in the realm of geology, and especially in the applied measures that can be taken to address climate change mitigation, specifically in Switzerland. And it's a great pleasure because I've worked with Larryn for 10 years, and to hear a culmination of much of his both theoretical and applied research today. It's excellent opportunity, I think, for you to pass this on, Larryn, to us, your knowledge. So thank you very much. And yes, as Shamli said, there will be 2 opportunities to ask questions. We'll do a break around 25 minutes in, and a first round of questions, and then some more questions at the end. So with that, I pass over to Larryn. Thank you, Larryn.
Thanks very much, Alana. Great. Welcome, everybody. It's a pleasure to be here in Lausanne. I was asked to kick off this new series of climate seminars dealing with geological applications that have something to do with countering climate change. So today I want to present to you an overview of how we can use Switzerland's deep geological subsurface for CO2 sequestration. CO2 is public enemy number 1, right? And also to obtain sustainable energy. I was asked to address a multidisciplinary audience with this talk, so I'm going to keep it very simple and try not to use too many geological terms. And for those of you, any geologists who are listening to me, I apologize for the simplicity. Be patient. And I understand that further seminars on this semester and next semester, we'll deal with more details of some of the kinds of projects I'll present to you today. So what are our challenges? We need to mitigate climate change and supply sustainable energy. The Swiss federal government has developed a strategy looking towards the year 2050 to reach net zero greenhouse gas emissions, and also probably by then to exit from nuclear power. Since 2018, no more licenses have been issued or will be issued for new power plants. So as soon as the existing 4 plants have to go offline, they've lived their lifetime, they will not be replaced. That's the current plan. So Let's look at CO2 emissions. CO2 is responsible for about 3/4 of the heating of Earth's atmosphere. That's the main problem we have to solve. Of course, methane is responsible for, let's say, about the last quarter. Switzerland emits about 42 million tons of CO2 a year. That's only 0.11% of the global total. Okay, so you could be excused for not worrying about it. However, there are various reasons, not less kind of responsibility to do something about this. Now, 9 million tons per year of this 42 are emissions from industrial point sources. Those are cement factories, municipal incinerators where your garbage is burned, chemical factories, oil refineries, wood burning plants, and so forth. These industrial sources of CO2 are classified by the Swiss Federal Office for Energy as hard to abate emissions. That means difficult to conceive of eliminating those emissions. These industries will probably have to continue far beyond 2050. For example, there's not enough space or desire to put urban waste in the ground. It also generate a lot of methane, which gets out. So hard to abate emissions. Do we have geological solutions to get rid of that CO2? Today, I'll present some of those solutions to you. Secondly, at the moment, around about 30% of Swiss electricity is nuclear. That has the advantage, it emits no CO2 or methane. It's continuously available 24 hours a day, every day of the year. And that's very different to solar and wind. Now, if Switzerland exits from nuclear power, there's going to be a gap in sustainable energy in the future. Can geological solutions help to fill that? Well, they can contribute something, and I'll explain that today as well. So that's more or less the scope of this talk. Let's now focus on geological storage of CO2 emissions. Firstly, I'd like to point out that CO2 capture in the industrial setting is a solved problem. There is existing expensive technology to capture CO2 before it goes out into the atmosphere. Okay, costs money, but it can be done. The big problem is something else, is what to do with that CO2 once you've captured it. Where do you put it? That is an unsolved problem. There are several solutions moving towards that, but that's our big challenge. It's a global challenge. Nowhere in the world can people at the moment solve this problem. We'll see that the geological solution is probably going to be the biggest, make the biggest contribution to this. So focus now on where to put the CO2. You might have heard of direct air capture, successful Swiss company. Yeah? They can capture the air, CO2 even from the air, at the moment only in small quantities, but where can one put it? So it's hidden away. There are some above ground solutions underway in Switzerland, entrapment of CO2 in concrete, for example, a couple of companies. CO2 mineralization is another approach where you can take magnesium, calcium, iron-rich materials. They could be rocks, for example. Allow them to react with CO2 in an industrial environment and make stable minerals like calcite, which are inert and can be just put out onto the surface of the earth without any problems. There are problems with these approaches. First, it's not quite clear if this approach in concrete is actually permanent enough for global change, climate change. And in terms of CO2 mineralization, the reactions need a lot of heat, high temperature, they're very slow, very expensive. And so at the moment, it's not yet feasible to do this at the scale required to have an impact on emissions. So let's look below the ground surface then and see what can be done. There are conceivable deep geological solutions. One would be to do the CO2 mineralization deep in the earth. So inject CO2 into rocks that are rich in these metals to create stable carbonates. This is being done in Iceland very successfully. Why don't we do the same here in Switzerland? This famous project called CarbFix. Well, in that CarbFix project, this is a drill core from there. They've drilled into glassy, that's rocks, basalt rich in volcanic glass. And as you see, very porous, good permeability. They can inject fluid, water with CO2 in it, waste CO2, and it forms underground calcite. Okay, why don't we do it? There are a couple of problems. We cannot do this in Switzerland. Firstly, we do not have glassy rocks. Glass is metastable in nature. It won't survive very long, and so it's very reactive. Yeah. In Switzerland, we have no glass in the subsurface, volcanic glass. It's all very tough, tightly structured minerals, which require high temperature and long times for reaction. Iceland is very hot in the subsurface, geothermal gradients of hundreds of degrees Celsius per kilometer. And we'll see in Switzerland, it's only 20 to 40 degrees. So that's really out of the question. So what can we do? There's another approach, which is being pursued worldwide, by the way. Inject CO2 into porous rock formations at depth between about 1 and 3 kilometers and hope it stays there forever. Sounds very scientific. There's more to it than what I'm saying, yeah? What kind of porous rock formations are we talking about? Well, these formations are actually called saline aquifers, and they're sealed by an impermeable caprock. And I want to explain what that is. Firstly, you might have seen in high school or university or wherever the principle of a natural gas trap. You're all familiar with using methane for cooking, right? It's of international strategic importance at the moment, you know, Russia's supplying, or Libya or whatever. Where does that come from? That comes from natural traps deep in the earth, in so-called trap structures. We have a rock which will not let gas or water pass through it. It's so impermeable. The grain size is so small, tightly packed minerals. And below it is a porous rock, which we call a saline aquifer, and above it sits the gas cap. When I was in school in New Zealand, I used to think, I'd seen those diagrams, I thought that was a big cavern like this lecture theatre, okay, and just full of gas. And it's not quite like that. So I'm using this high-tech analogy here. You may have used sponges like this in the kitchen. I stacked up a few. That's like our stratigraphy, okay? Now, bear with me, it's not such a great analogy, but these green layers should be impermeable, okay? Don't let any water through or gas. Now, if you fold them like this, you can make a fold that looks kind of like that, and you dip it in a bit of water, the water will rise up here. You've got water below, and you've got gas, in this case, air in the kitchen on top, okay? So what I'm trying to convey to you is that these rocks are all solid rocks here. There's a network of pores inside the rock, which is extremely strong, made of mineral grains. You take any sandstone that you find in the city, put a few drops of water on it, you'll see the water moves into it, okay? They're porous, and that's what this analogy is. In reality, these impermeable cap rocks are clay stones or salt layers, and the saline aquifers are usually sandstones, fractured limestones, or porous limestones and dollar stones. Why does the aquifer have to be saline? Well, we have freshwater aquifers. An aquifer is just a rock which allows you to, water can be moved through it by pumping. That's the definition of an aquifer. We don't want to damage freshwater aquifers. They're the most precious resource we have below the surface of the earth. So the idea is to only consider for gas, for say CO2 storage, aquifers which are saline, because that water has got no other purpose. There's no conflict of interest. Okay, under the microscope, these sandstones look like this. This is just 0.1 millimeter scale here. We've got sand grains, okay? And between them, what this blue material, which is actually stained blue epoxy here, in nature, those are the pores. They connect with each other, a lot of pore space, about 22 volume percent. And because they're connected, we have a permeability. The units we use in the business are millidarcy, about 1,000, so almost 1 darcy here. That's a good reservoir rock, and that sample was taken from a deep gas reservoir in the North Sea. Okay, now is sequestering CO2 in deep saline aquifers a crazy idea? Let's see. I'll give you some facts. Firstly, there are certain saline aquifers that can store fluids forever. I'm defining forever as longer than 500 million years. It's a good time, right? You agree? Here is a histogram showing where the world's gas and oil reserves, all natural, in which the age of those reserves, okay? Now we have most, as just a histogram with the percentages, most of oil and gas here comes from 100, let's say 100 to 200 million years ago. It's the age of the gas and the oil. It's been sitting in the rocks for that long. But we even have some oil and a little bit of gas around over 500 million years in age. Right. So nature's telling us something. Rocks can preserve fluids forever. All we have to do is copy nature, right? Some deep saline aquifers contain fluids at high pressures. There you go. There's an oil gusher. It's proof that it's under high pressure. And if you don't do anything crazy like drilling into it at the wrong time and don't control it, in 1910, they didn't know how to control the pressure. It'll come out. Okay, some deep saline aquifers contain pure natural gas, pure natural CO2 gas under high pressure. So, give an example, not far from here. Here's Grenoble. Here's a place called Montmiral and all these stars. These are natural reservoirs of almost pure CO2. Those reservoirs are about 35 million years old. They've been sitting there all that time. And what is crazy is at the moment, that CO2 is being pumped out and used for the food industry. Okay, so another fact, since the 1950s, hundreds of geological gas reservoirs have been used, have their natural gases being pumped out in the winter and burned, and then refilled with gas imported from somewhere else, maybe from Siberia, maybe from Libya, okay? Reused every year, hundreds of reservoirs. Here's a map showing these reservoirs in Europe, around Switzerland, but Germany, France, Italy, and Austria all have these reservoirs. There haven't been any leaks from these, okay? Right, so let's conclude then that nature can be successfully copied. This is copy or using reservoirs to store gas in the geological subsurface safely and permanently. I hope you're convinced. Today, worldwide, this is the main approach being taken to get rid of CO2 permanently. Pump it into underground into saline aquifers. There are about 65 commercial projects underway at the moment. More than 45 million tons. That's the yearly output total of Switzerland is being sequestered each year. It's ramping up from year to year. A giant capacity is foreseen, has been estimated by geologists, thousands of gigatons. Remember, the annual production worldwide is around about 37 gigatons. So you need a lot of years of production there. Good. So the next question, okay, well, let's do it in Switzerland, okay? Do what everyone else is doing around the world. First thing you have to do is find that trap structure underneath the ground, and you do a seismic survey. If you see something like that, it'll be a surprise, but the principle is the same as ultrasonics, right? We do a seismic survey and looking at reflections from vibrations set off at the top surface of the Earth, you can see, for example, fold structures. And then in the case of Austria, where there are big natural gas reservoirs, it really does look like this. Huh? In Switzerland, there are a few cases where we have the same structure, but in Switzerland, no gas. That's a pity, that's disappointing. There is no oil and gas industry, has ever been really in Switzerland of notable quantities. Yeah. So in Switzerland, if we find these right structures, we're going to have to create our own gas reservoir. The way we do that is inject gas, push it in, push it down. And when we inject the gas, we're forcing away the water out of that sponge-like saline aquifer. That water has to go somewhere. Keep pumping, keep pumping. It might move out and lubricate faults nearby and cause an earthquake. It's possible. That has to be taken into account. Yeah, if the reservoirs are very big, the pressure just dissipates, and there's usually not a problem. Anyway, there are criteria one can establish for these gas storage sites deeper than 800 meters. They need a nice cap rock, no leaky faults, and so forth. Now, there is Switzerland's largest saline aquifer is called the Muschelkalk. This is a map of northern Switzerland. The Alps are down here. Here we are in Lausanne today. There's Geneva, there's Zurich, right? This aquifer lies at depth below all of the Swiss plateau. And it consists of a porous dolostone. There are big pores in some of these drill cores that we obtain from that aquifer. So that's a possibility then to store, inject CO2 there. We did an analysis of that together with Arthur Adams is here in the audience with us to see which part of this aquifer is really suitable, which fulfills the criteria that I listed before. And it turns out that unfortunately, only this green band along the top has high enough porosity and permeability for this technology. Still, you'll see these yellow lines of faults. We have to work our way between them, find fold structures. It's not easy, bit of a challenge there. There is a theoretical storage capacity of about 52 million tons of CO2, which is not a lot, actually, right? 5-6 years of industrial emissions in Switzerland. It's not big. This is just one aquifer, though. There are others around in the stack of sediments in the north. Okay, so what is the status of this geological approach to store CO2 in Switzerland at the moment? Firstly, no storage sites have been verified yet and tested and say, yes, we definitely have a site here in this spot. We definitely have a site there. We aren't there yet. Exploration and verification requires about $40 million for one site, and it takes about 12 years to do it. Maybe we'd have to test 5 sites to find one good one or 2 good ones, right? So you see, it's a bit of a problem. So far, there's no funding for large-scale exploration because sequestering CO2 is not really a profit-making business at the moment. It's becoming more profitable with time. So companies are reluctant to try this. And why should the taxpayer pay? You know, that would be the alternative. Maybe the taxpayer should pay because it won't happen otherwise. And all the while, time is passing and atmospheric temperatures are rising. We have to do something with this CO2, stop emitting it. So that's the situation we're in. Starting in October, so in a couple of weeks, we have a new project underway. It's called CITRU. And the purpose of that project is to go to a site, inject some CO2 up here into the Muschelkalk aquifer in our green zone. And it's like a rehearsal. We're going to rehearse how to plan this project, all the science for it, operational issues, legal, social issues. Yeah, we don't have a good trap structure there, but we do have a free, open borehole that we can use for this. Okay, so it's a consortium of different players, as you see down here, and yeah, we'll see how that goes. And basically, this is just knowledge which would help us accelerate exploration for real storage sites. Now, there's another use of saline aquifers, which is interesting. A way to store renewable energy, it's called geomethanation. Excess solar and wind energy, as we know, is difficult to store over time, right? There aren't batteries which can take that amount of store that power, say from sunny summer days into the winter. So there's a strategy is to use the excess solar energy to split water by electrolysis, break up water into H2 and oxygen. At the moment, the hydrogen market, of course, hydrogen you can transport, burn in all kinds of, use for as an energy source. However, the hydrogen market is very small compared to that of the methane market at the moment. That's city gas, natural gas is methane, okay? But all the pipes and infrastructure exists. So the company RAG in Austria, that's one of those companies with natural gas reservoirs, decided why not, and until the hydrogen market develops, why not convert this excess hydrogen, green hydrogen it's called, into methane and burn it in burn it in existing infrastructure in a CO2 neutral way, as a kind of like a transitional technology until the hydrogen market develops. Well, as we know, huge volumes of methane are best stored for seasonal use in geological reservoirs, and the same applies to hydrogen. Yeah, if we're going to use hydrogen in the future in a big way, we're going to have subsurface storage facilities for strategic and economic reasons. We can store vast amounts there. It's very hard to store a lot of hydrogen above on the Earth's surface because it's dangerous to pressurize it. So this is the now patented process of RAG. Take green hydrogen, take waste CO2, which needs to be sequestered, inject them both into an existing natural gas reservoir. And what happens is they found this by observing, just by accident, natural microbes, methanogenic microbes, take that hydrogen and CO2 and spontaneously convert it to methane and water. They live from that reaction. And so there's a huge boom in the number of those microbes. Such microbes are present in all shallow saline aquifers around the world. A huge variety of microbes. There's life below the surface, life in rocks, okay? They discovered this they wanted to test storing hydrogen, and they noticed when they pumped out after a while the hydrogen, they'd lost some of the hydrogen but gained methane. Then they realized what was happening. That's been patented, and that reaction takes place in 3 or 4 weeks. There's a nice paper of it just came out this year. Okay, so that's a very interesting cycle. You can take that methane which is produced, sell it conventionally. A user could burn it, generate CO2, of course. Each mole of methane you burn generates a mole of CO2. Let that go into the atmosphere. All right, you haven't stopped emissions, but you're actually making use of this excess energy. Another way to do it is if there is a usage for this methane near the site, and it's burned there for whatever industrial purpose, that CO2 could be captured and recycled. And so that would make it actually, the first case would be CO neutral, and the second case would be basically CO2 free. Okay, so that's underway now in Austria, and we tried to evaluate whether that could apply to Switzerland. It basically is the same kind of reservoir we'd have to find as for CO2 sequestration. Right, back to the Muschelkalk aquifer as an example for gas storage, be it CO2 or hydrogen or for geomethanation. which gas should we be storing underground if suitable sites turn out to be rare in Switzerland? Now, CO2 storage sites can never be used again for anything, right? You fill it with CO2 and you leave it there for 1,000 years until humans have developed a solution to the climate problem. Nuclear fusion or something. If we only have small sites, 1 or 2 sites are found, and we fill it with CO2, that will have very little impact on total emissions far into the future. It'll be negligible. So maybe we shouldn't do that. Geomethanation is an interesting transitional technology towards the widespread use of hydrogen. It uses exactly the same reservoirs as CO2. Actually, you can go to greater depths with CO2. This has to be shallow, so the rocks are not too hot. Above 60 degrees, the microbes can't survive, okay? So you can go to higher temperatures with CO2, but they're basically in conflict with each other. Finally, I think Switzerland needs, for strategic and economic reasons, to have seasonal hydrogen storage available underground far into the future. Switzerland's a small country, yeah, under pressure, you know, geopolitics. It's good if it has its energy reserves underground, ready to be used, keep us warm in the winter. So who decides the priority of use of subsurface storage space? That's an interesting question. Now let's talk about our second challenge with sustainable energy sources. How can we use the Earth below the subsurface as a source of sustainable energy? And there's yet another use of saline aquifers, and that is to store excess summer heat for the wintertime. This also is could be in conflict with use of the subsurface in a certain place for CO2 storage or hydrogen or methane. Now, heating buildings in the northern hemisphere has a very irregular, well, say cyclical variation in demand, okay, of how much energy is required. Obviously, it's cold in winter, it's warm in summer. There are certain energy supplies which are usually designed to be constant supply, hydroelectric or whatever. In any case, there is certainly an excess potential here where you have excess energy production in summer. If that energy could be stored for the winter and reused, you can manage your energy budget a lot better. So this, the Netherlands has now developed more than 3,000 underground operating systems where they store hot water in the subsurface. In Holland, it's in actually sands, loose sands. They're full of water, but they're not lithified. They're not like hard rocks. That's to do with the geology of the Netherlands, okay? This is they're low temperature deposits of sand, but there they can store energy and take it out in winter. They use it extensively. But of course, there's potential to go up higher, anything up to about 90 degrees. If you go higher, you get close to the boiling point of water when you extract or inject the heat through hot water, and that makes it much more complicated. So the principle of this, it's called, this technology is Aquifer Thermal Energy Storage, or ATES. The idea is you have drill some holes into a porous aquifer, right? Saline aquifer, probably. You can use a freshwater one, but saline's better. You have your excess heat. You inject that in the form of hot water in the summer, and you heat up the rocks. The rocks have got a huge heat capacity, heat up very slowly. By the way, it takes years to heat up those rocks. So you might start off injecting at 90 degrees, but that will cool down, of course, by the heat capacity of the rocks. So it takes several seasons to get up to your target temperature. In winter, when you want to use that hot water, you just pump it back out again. That requires that the heat is still there. the groundwater flow has not taken the heat 3 kilometers downstream, okay? Anyway, so we're developing this scheme in Bern now, in the city of Bern, at the place called Forsthaus, which is the site of an energy center for an energy provider, EWB. It's a site where they burn municipal waste. Of course, that waste is pretty much constant throughout the year, so they have a lot of excess heat in summer. The idea is to take that excess heat, put it through a heat exchanger, and heat up water, inject it, wait till winter, bring it out again. When they bring it out, they want to distribute it through the existing urban district heating network. The reason that this company is financing this is because they don't have enough heat in winter. And they have lots of heat, which is going up into the atmosphere actually in summer. They do not have enough heat for the winter demand. And so they burn wood, which creates CO2. And at times they need to burn gas in a turbine to make up the deficit. So the idea of this project in Bern is to eliminate those additional heat sources in winter and trap their excess heat from burning waste. So this project has been going on for a few years. It's been slow and difficult. We now have 2 boreholes down between 240 and 530 meters depth in our target rock formation. These are just geophysical logs. When you drill the well, you lower down like all kinds of measurement tools, and it tells you all kinds of things, physical properties that give you an idea of the density of the rock and the porosity and the permeability. We've also taken core out of one of these wells. And these 2 wells are only about 40 meters apart at the bottom. We've found that the rocks that were intersected, this sort of layer cake structure, the yellow ones are big sandstones. The same formation outcrops on the surface, about 15 kilometers away from Bern. We see porous sandstones, impermeable claystone, sandstone, claystone, sandstone, claystone. That's the sequence of rocks which deposited in old rivers that were active about 20 million years ago in front of the Alps, taking down all the erosional material. And so the porous sandstones are the targets to store the heat, like this one here or that one down there. At the moment, the status at the moment is that we've obtained hydraulic connectivity between the wells along one of these sandstones. Unfortunately, the permeability is low. It's a bit too low for the application in mind. And so what we've done is, at the moment, we're injecting, even today, carbonic acid, CO2 and water, to enhance the permeability. The low permeability is actually due to a little bit of calcite, diagenetic calcite for the geologists in the audience. So we're trying to dissolve that and enhance the permeability. So that's an ongoing story. Maybe it'll work, maybe it won't. Okay, but I think you understand, if this works in Bern, that system can be cloned through a lot of Switzerland. That would be a great advantage. Let's talk about the deeper areas of the subsurface and geothermal energy. Now, you know that temperatures increase as you go deeper down in the earth. That's mostly due to radioactive decay of naturally occurring potassium, uranium, and thorium, which are present in many rocks. That's why the earth gets hotter. There's a little bit of heat left over from the original accretion of our planet, but that's only a fraction of the current heat flow. Now, if we look at a map of, again, northern part of Switzerland, these different colored areas show the different rates of temperature increase with depth. So they vary from above 35, where the maximum is about 45 degrees up here, down to 30 degrees or even less in this part of the Swiss plateau, under the Swiss plateau. In the Alps are cold. okay, 25 degrees per kilometer. So this means that if you want to reach high temperatures, for example, if you want to generate electricity from heat, you need to drive a turbine at higher temperature than 120 degrees. So that would imply drilling to greater than 4 kilometers depth. Do that. If your aim is to produce electricity, that's very expensive. And otherwise, of course, you can use it for heating at shallower wells. And on the right, we see a map, which is the current situation there. All these projects are underway in Switzerland. The gray ones are abandoned because something went wrong there. But all the others are underway trying to make use of this natural heat in the subsurface. So basically what you do is drill down, and again, most attempts to get the heat out use water as the medium to transport the heat. You inject water you can inject water down a borehole, or you can use natural water to carry the heat out. So there are a lot of different situations in the subsurface of the Swiss geology, which can be targeted in geothermal exploration. The first is what we call aquifer hydrothermal systems. Those are our saline aquifers, yet again, where they have hot water that can be, in some cases, pumped straight out of the aquifer. Here are some of the well-known aquifers that might come into question for that. Here's the Muschelkalk again, which we've talked about. By the way, this cross-section, here's an overview of northern Switzerland. If we make cross-sections like this, northwest, southeast, okay, then going towards the Alps. So that's an example from northwest to southeast towards the Alps. This is a cross-section of the geology down to, that's a total here, like 8 kilometers, right, of depth. The vertical exaggeration is very high. Of course, they're not the same scales, vertical and horizontal. It's just schematic. But we see we have these granitic rocks, basement rocks they're called, overlain by layers of sediments, which are younger, and the basin filled by debris from the eroding Alps. So aquifer-hosted hydrothermal systems is one type. Others are fracture-hosted. For example, big fractures here or faults can also allow water to circulate deeply, release deep water, or allow shallow water to circulate. And then combinations of these as well, combined aquifer and fault hydrothermal. And I'll also give you an example where water is not involved, no natural water is involved, okay? So these three types involve natural water. There's also a process to extract heat from the rocks just by injecting surface water, river water or whatever. Okay, back to, I'm using this Muschelkalk aquifer again because we've already seen the map. So that's this yellow, actually the yellow curve, yellow layer up here, which dives down as we go towards the Alps. These rocks get progressively buried. So at the moment in the Muschelkalk, it's not shown up here, but there is Muschelkalk present. There's been since, I think, 1993 or 1994, a very successful aquifer hydrothermal system operating at about 65 degrees water, produces 70 cubic meters an hour. It's at 1,500 meters depth, and that's been supplying district heating to the village of Larryn, which is basically part of Greater Basel, for 30 years. It's a very successful project. There's another one at Schlattingen, 60 degrees, 20 cubic meters per hour. That's being used to provide heat for grow tomatoes in a giant greenhouse. I visited there recently, and it turns out tomatoes are the most lucrative crop per square meter at the moment. The most valuable thing you can plant per square meter. And the energy requirement is high, of course, and so all that energy coming out is used for heating. Now, we're in the northern part of the aquifer here, and as we go south, a deep and very costly drill hole was drilled into the Muschelkalk aquifer to try and find something like these two cases at a place called Triemli in Zurich. And it turned out to be essentially dry. You get a cup of warm water every 10 minutes. And that rock is just not permeable enough. So something's going on. If you look at now the evaluation that I did with Arthur and our other colleagues, you see this is in the red zone. This is in the zone where we found out there's just not enough porosity and permeability. And the reason for that, the reason this aquifer and all the others which are lying above it or below it, at least say deeper aquifers here, will behave the same way. As we go deeper, the pores collapse under this huge weight of sediments, okay? So the same rocks here are only 1,000 meters below the surface. Down here, they're about 6 or 7 kilometers below the surface under a huge weight of overlying rocks. So these photographs show, let's see that little, where I'm moving the cursor now, that small band is 200 micrometers. So where the dark areas in this image from the standing electron microscope show the pore space. At shallow depths, just 100 meters, there's lots of pore space. If we take another sample, these are from drill cores, deeper and deeper, we see the amount of black area reduces and vanishes at more than about 2 kilometers. And that's the problem with the aquifers. That's due to the geology, the history of building the Alps. So it's no good for those saline aquifer applications. That's something we have to live with. And this process is part of the reason why Switzerland has never had a bigger oil and gas industry, yeah, with traps and so forth. Okay, let's now go to, I'm going to jump back and show you now these fault-hosted hydrothermal systems. You might know in the Rhone Valley, here is Martigny's down here, there's Lac du Main here. There are lots of hot springs, okay? And they're all formed by the same process. There's actually surface water, rainwater, meltwater from snow is infiltrating down into large faults. And it sort of makes a siphon. You've got, perhaps I'll just point out some areas you've heard of: Leukerbad, Briedebad, Lavey-le-Bain, a famous hot baths you can go and visit and swim around in, right? But they can also be used, there's a lot of interest now at all these sites to make more use of this water for heating, alternative sustainable energy source. So we're also involved in an exploration program at the moment funded by the Swiss Federal Office of Energy. Now, here's a diagram from, we here at the Grimsel Pass, which you might know, the Central Alps on the border between Bern and Wallis. There's a cool example, one of these giant faults, where we've more or less, we did a special research project on it and showed that meltwater, rainwater is infiltrating to great depths, 9 or 10 kilometers, is picking up heat from the rocks. I mean, that's only 25 degrees Celsius per kilometer. Because we go to 10 kilometers, that water gets quite hot, okay, over 200 degrees. And then finds its way back up, running along that same fault plane. A lot of these fault planes are permeable, irregular permeability, but permeable. So infiltration, that means that the water goes into the fault at high altitude, and it's just like a siphon. It's going to pop out. It can go deeper than its discharge site, but it's going to pop out in low areas, valley floors, everything. And along at Grimsel Pass itself, even though that's a high pass, it's a low point. Here the fault is not permeable, it's blocked. So the water comes out here right on the pass. We also calculated just by modeling the amount of heat which is being stored in the rocks, how that heat is distributed in depth. So these areas here, orange areas are kind of, there's a lot of heat. This is in kilojoules here, 10 to the 13 kilojoules. A lot of energy is stored. This system has been going on for more than 3 million years. It's heated up a lot of rock. So as well as having, in this case, a rather modest amount of water coming out, in fact, it's surrounded by a large plume of hot rock. So that's the way these systems operate. And if you go back here and imagine under all these locations, there's something similar happening, there's a lot of potential to exploit that heat. I'm moving ahead. I think this is my second to last slide. I don't know. Oops. Okay, the last one, let's go back to the system of hot, dry rock where natural water doesn't play a role. It's called, they're called enhanced or engineered geothermal systems. And the idea is to drill into rocks where there are no faults. And in fact, to rocks which are not permeable to water. The aim is to go to much higher temperatures than 120 in order to generate electricity and excess heat. So the way this works is that the permeability of the rocks has to be created by hydraulic stimulation. So it means there's a slow process of injecting water from the surface, and it creates a network of microfractures. You drill a hole, you then inject a little bit of water and make a cloud of microfractures, okay? Basically, these rocks have fractures in them, and by slightly increasing the water pressure, like you said, it's like a hammer. Water is not very compressible, or under these conditions, say at 150 degrees, it has a certain compressibility, and that will open these existing fractures. When they open, there's a little bit of movement, microseismicity. When the pressure releases, those microfractures cannot fit together again. Okay, when they come back, there's a mismatch, and so they've created pore space. The reason that they don't come back together is because there are far-field stresses on the subsurface present everywhere. Okay, then you make your first stimulation area, then you drill further and put in packers. You block your hole here. You can block off this area with packers and then inject water through the middle of them and create another area, okay? And so once you have sort of clouds of these microfractures, then you drill your next well through that cloud to connect them. And then you can circulate cold water in, it picks up heat from the rocks, and you pump it back out, hot water. Now, this has been successfully demonstrated in Utah in a project called Forge, which is fascinating. You can find that on the internet. What's happening in Switzerland? An early attempt to do this in Basel City, you may remember this, was stopped in 2009 because the first time they tried to inject the water, they generated a magnitude 3.4 earthquake, which was not appreciated by the city of Basel. There was $6 million worth of damage or claimed damage. Who knows if that crack in the wall was there before or after the earthquake. In any case, that project was killed straight away. It was the first attempt. It was a great project. No one got hurt, luckily, and the geological community learned a lot. And so there's a new attempt underway today at a place called Otzon in Jura. And the first well was successfully drilled. That's this one here. Actually, it's actually still vertical, down to 4,000 meters, okay? And within the next half year, the tests will be made, stimulation will go underway, and then probably late next year, the next well will be drilled, and we'll see if it works. Okay, so there are many challenges for geothermal energy. As we've seen, aquifer geothermal systems, there's collapse of the porosity and the Alps. It's difficult to predict the presence and permeability of fracture networks. The fault-hosted systems, again, if you're in this kind of system, it's very hard to know exactly where the water upflow region is. The recent deep well at Larryn missed the water-bearing fault, just drilled into the hot plume of rock around it. Very hot rock, but dry, okay? And of course, earthquakes can be generated by water injection and extraction. They have to be avoided. And the status at the moment in Switzerland overall for geothermal energy, there are 14 new exploration projects underway. It has never been so active as it is today. That's a response to the energy strategy of the federal government, which is also heavily subsidized for companies. So from what we've seen, there's a high potential for aquifer geothermal systems on the northern margin of Switzerland, where the porosity hasn't collapsed. And we'll see what happens to this hot, dry rock project. Okay, so I wonder if I can maybe escape. And can you see that? Water gushing. That's a successful well in Geneva, 35 degrees at 700 meters, 50 liters per second. Geneva is a great place for this on the margin of the basin. And so I haven't gone into details on these projects, and I hope that in the coming seminars, specialists will give you the details. And I'll stop here for lack of time.